Stan Gibilisco here to talk a little bit about a coordinate system that I devised when I was only about 16 years old in 10th grade at John Marshall High School, Rochester, Minnesota, to graph functions all the way to infinity. I already showed you a polar coordinate scheme that works according to the similar principle of geometric compression. I call it an infinite rectangular coordinate system in this case because instead of a polar plane, it is a rectangular plane. I wouldn't call it Cartesian exactly because I doubt that Rene Descartes thought this up or had any use for it at the time. But what you do is you take your axes. Here's your origin right there. The x equals 0, y equals 0 at the center, just like a conventional system. Then 1 is halfway between 0 and infinity, geometrically halfway. 2 is halfway between 1 and infinity. 3 is halfway between 2 and infinity, and so on for the positive x-axis. Same for the positive y-axis. The negative x and negative y axes are just the opposite. There's -1, -2, -3, and so on. For y, there's -1, -2, -3, and so on. For x, so you get a complete rectangular coordinate system. At the very ends, at this dashed rectangle, and I've drawn it as a rectangle here, or actually a square in this case, are the values where one or the other or both of the coordinate values equal either infinity or minus infinity. Y equals plus infinity, y equals minus infinity. Now, the question as to whether minus and plus infinity are the same thing is a subject for an entirely different discussion. But here we're going to assume that they are different. Now, suppose that you graph a function on this plane. Just an ordinary function. Let's make something very simple. Y equals x. A straight line function where y equals x, you're going to get a line that runs diagonally through the square, and it'll be straight, just like that. So far, it looks just like the Cartesian system, doesn't it? Suppose that we want to graph y equals 1. In that case, we get this. If we graph, say, x equals -2, we'll get, there's -2 for x, a vertical line like that. And they're all straight, just as they would be in Cartesian, ordinary Cartesian coordinates. However, that's where the similarity pretty much ends. Suppose that you want to graph y equals 2x. Well, you can plot a bunch of points. 0, 0. Okay, if x equals 1, y equals 2. So we're up here. If x equals 2, y equals 4. So we're up here. If x equals 3, y equals 6. In this rendition, we're almost to the dashed line. Same down here. If x equals -1, y equals -2. If x equals -2, y equals -4. If x equals -3, y equals -6. And so what you're going to get is something like that. It's not going to be straight anymore. If the slope of the line is not either 1 or -1 or 0 or infinity undefined, then you're going to get a curve rather than a straight line. If you were to graph now, say y equals 3x, the situation would be exaggerated even more, and you would get a compressed plane or a compressed line that would look more like this. And as the coefficient here were to increase, say y equals, well, I'm trying to erase this. It just doesn't want to do it sometimes. These programs just don't want to behave themselves. Y equals 100x. Well, in this graph, for all practical intents and purposes, we'd get something that looked like this. Would almost be squared off. Not quite, but almost. And so on and so on. Now you can, of course, change the fundamental or initial value here from 1 to something else. Maybe you'd want to make this 10, 20, 30, minus 10, minus 20. As long as you keep doubling the value on the coordinate axis every time you go halfway to infinity. And of course, these infinities then will all be just the same infinities as they would otherwise be, because 10 times infinity is infinity, and you know the drill, right? It's kind of intuitive. I haven't rigorously proven that, though, that 10 times infinity equals infinity. I'm just asking you to take that on faith. 10 times infinity equals infinity. 10 times minus infinity equals minus 10 times infinity equals minus infinity, and so on and so on. Infinitesimal arithmetic. S with two S's, infinitesimal. Which is a word that I invented not knowing that there was such a word as infinitesimal. Infinitesimal, meaning having to do with infinity. So I think you've probably just about devoured enough stuff now having to do with infinity. But play around with the system like this. Or you can make one axis linear and the other one compressed. You know, semi-infinite, semi-infinite, what's semi-infinite? I mean, like either you're infinite or you aren't, right? Stan Gibilisco signing off. Until next time, so long.